Hey guys, and welcome back. So now we're going to be taking a look at the inverses of a matrix. Okay, so the inverse of a matrix, well, first thing we need to be able to identify before beginning our actual lesson on inverses of matrices, we need to build up to it a little bit more. So first we're going to talk about the identity matrix. So that identity matrix, guys, we've actually been creating. Okay, remember when we've gotten things into reduced row echelon form? That's when we have ones along the main diagonal and zeros everywhere else. So we've actually already been doing that. This is almost identical to when we did reduced row echelon form. Reduced row echelon form, where you have ones along the diagonal and then zeros everywhere else. Okay? So we actually just call this the identity matrix. That is the identity matrix. So why do we call it the identity matrix? Well, let's take a look. If we let A, so matrix A, equal the following, let's compute. I have A times the identity matrix. This sub 2 means a 2 by 2. Identity matrices are always a square matrix. So this is really I sub 2 and then I sub 3. Again, identity matrix is always a square. So let's compute. I have A, which is A, B, C, D, and it's getting multiplied by the identity matrix with a square matrix of 2. So that's 1, 0, 0, 1. When I multiply these, so we're going to do some matrix multiplication. Let's see. A times 1 is A. B times 0 is 0. So we have A plus 0, which is just A. All right. Again, we have row by column. A times 0 is 0, plus B times 1, which is B. Next. Second row, first column, C times 1 is C. D times 0 is 0. All right? And then lastly, I've got CD times 0, 1. C times 0 is 0. D times 1 is D. So there you have it. When I multiply a matrix by the identity, I'll get right back to the original matrix. So here I multiplied A by the identity, and I ended up with just A. All right, well, let's take a look and see if that's going to be held true for I2, so identity matrix of square matrix 2 times A. So let's see. I have 1, 0, 0, 1, and let's multiply it by A, B, C, D. When we do our multiplication here, A times 1 is just A, plus 0 times C, which is 0. All right, next, I have row by column. 1 times B is B. 0 times D is 0. Next row, 0 times A is 0. C times 1 is C. And lastly, 0 and 1 times BD. 0 times B is 0. 1 times D is D. So it does, it holds true. We can conclude that the identity matrix commutes with everything. It's actually really important. The identity matrix commutes with everything. So if we take a look, if I were to consider the multiplicative inverse of A, what would you guys tell me the multiplicative inverse of A would be? Good. We would say 1 over A. Because A times 1 over A is 1, and 1 over A times A is 1, where 1 is the identity element of multiplication. Okay? It's going to be pretty crucial for what we're going to be doing. All right? All right, let's continue through. All right, so bear with me here. This is going to be a rather more step-by-step process here. So let's take a look. Again, remember, only a square matrix can have an inverse. Okay, this would not work by a 3 by 2 or a 2 by 1. Doesn't work. Remember, you have to be able to use that identity matrix where there's ones along the diagonals and zeros everywhere else. We could have also done this for a 4x4, okay? And hopefully you guys get the idea. All right, so this is only going to work for a square matrix. All right, so let's take a look at the first example. We have let A equal the following matrix. We want to find A inverse. All right, well, I'm going to let A inverse equal that ABCD we had from before. All right, so what we know is the following. We know that A times its inverse is going to get me back to the identity, right? So we just said that earlier. That's over here. If I have, for example, we had the inverse of A is 1 over A. So if I have A, multiply it by its inverse, I'll get back to the identity where we had 1s across the diagonal. All right, so let's get to it. So we have A times its inverse is going to be the identity. And we're dealing with the 2 by 2, so that's I sub 2. Okay, well, we know A. We have A is equal to, we have 2, 4, 1, negative 1. We don't know the inverse. That's what we're going to find. So we're just coming up with variables. We've got A, B, C, and D. So we're going to multiply it by A, B, C, D. And the identity matrix is going to be 1s across the diagonal with zeros everywhere else. Okay, so I'll repeat that one more time. We have A times A inverse is going to get us the identity matrix. We're multiplying A times, we don't know what the inverse is, we're going to find it, and we're setting it equal to the identity, where identity has 1s along the diagonal and zeros everywhere else. Okay, so let's take a look at what our next step is going to be. Now, let's multiply. I have 2, 4 times AC, so we'll have 2 times A plus 4 times C, again, matrix multiplication, which we did as one of our first lessons. Again, row by column. 2 times B is 2B. 4 times D is plus 4D. Again, now let's look at our next row in our first column. 1 times A is just A. And negative 1 times C is just negative C. And then we have last row, second column. 1 times B is just B. And negative 1 times D is minus D. Okay? And this is all equal to that identity matrix of 1, 0, 0, 1. Now, we're going to break this up into 2 matrices because we know the following. I know that this column is equal to this column, and I know this column is equal to this column. So let's separate them. I'll have 2A plus 4C equals 1. I have A minus C equals 0. So that's from here. And now I have here is equal to here. 2B plus 4D equals 0. And B minus D equals 1. Okay, well, I can create now 2 augmented matrices from this. So let's write, we'll have 2, 4, 1, 1, negative 1, coming up with the augmented matrix. And then from here, I will have 2, 4, 1, negative 1, and 0, 1. All right, so far looking good. Now, our next step, what we're going to do is, do you guys notice how these numbers in this 2 by 2 matrix matches? Okay, because they have the same coefficients, that allows us to doubly the augmented solutions. Okay, so I'm going to write that out. Because they have the same coefficients, that allows us to doubly the augmented solutions. Okay, so that means I'm allowed to write 2, 4, 1, -1 is equal to the following combined matrix, 1, 0 with 0, 1. So we're going to write that here, 1, 0, 0, 1. By a series of row operations, I'll end up with 1, 0, 0, 1, and 1/6, 2/3, 1/6, and -1/3. Okay, so let me just explain really quick. Just when you go through row operations here, guys, all right, really what we're trying to do is get this right-hand side of the 1, 0, 0, 1. We're trying to get the identity to get over to the left. And you do that by going through a series of row operations. So I'd be happy to go over that with you guys over Zoom, through Remind, etc. I just don't want to spend too much time on here doing that. All right, so after going through that series of row operations, after you get the identity to be on the left-hand side now, this is now my inverse matrix. So to find that inverse, so that's now my A inverse. That's our inverse matrix. So to find an inverse, okay, we have A, where A is on the left-hand side, and the identity matrix is on the right, as shown up here. So A is on the left, identity matrix is on the right. Through a series of row operations, we want to reverse that, where we have the identity matrix on the left and the inverse on the right. Okay, so in the end, our answer here is that A inverse is that 1/6, 2/3, 1/6, and -1/3. Okay, this is just one way that we solve matrices by performing inverses. There's another method I'm also going to show you with inverses as well. Okay? All right, let's keep going. So why don't we do an example now together? Let's do example 2. All right, so we need to know our steps. Our first step is we want to doubly augment with the identity matrix. Okay, and remember that identity matrix is a 2 by 2, so I sub 2. And we want to use Gaussian, I know your favorite, Gaussian elimination to get the identity on the left-hand side. Okay, LHS means left-hand side. And then our third step is we want the matrix to be on the right-hand side. RHS means right-hand side. So I'll read these steps out one more time for us. We want to doubly augment with the identity matrix. We're going to use Gaussian elimination to get the identity matrix on the left-hand side. And then the matrix will be on the right-hand side. All right, so let's just get to it. Let's create our matrix. Again, we have doubly augment the matrix. So we have 2, 3, 1, 2, where we have 1, 0, 0, 1. On the other side, that's the identity. Okay, first step now, guys. Remember our end result is we want 1, 0, 0, 1 with all the numbers on the right-hand side. This will be our inverse matrix. So that will be our A inverse. Okay, so remember, this is the goal. Keep the goal in mind. All right, so let's get started here. First thing we should probably do is switch row 1 and row 2, because we want to get that into reduced row echelon form. I want that first number to be a 1. And our first number in the second row is a 1, so why not just switch the rows? So we'll have 1, 2, 0, 1, and I have 2, 3, 1, 0. Okay, now our next step is we want to turn this 2 into a 0. So the way that we're going to do that is we're going to multiply the first row by -2 and add it to the second row to get our new second row. So again, multiply the first row by -2, because when I multiply the first row by -2, watch what happens. I'll have -2, -4, 0, -2. Remember, it goes to everything. That -2 you're distributing goes to everything. Okay? And now nothing happened to the second row. We're just now adding them. So I have 2, 3, 1, and 0. And we're just adding these things. As we wanted, these are going to cancel to 0, which is good. We'll have -1, 1, and -2. So now that's my new second row. So let's write it out. Okay, again, now nothing changed with the first row. We didn't do anything to it. Now, guys, remember our next step. Again, remember the goal. We want 1, 0, 0, 1, and we'll get the numbers on the right-hand side. The numbers on the right-hand side, that's going to be our inverse matrix. That's our goal. Okay, now, our next step, I'm just going to erase this just for some space. We want to multiply the second row by what? I want that to turn into a 1 now. So what should I be multiplying the second row by? Very good. We're going to multiply the second row by -1 to get our new second row. So nothing changed about the first row. And I'll have 0, 1, -1, 2. Awesome. All right, so far so good. Next piece, remember, we want our matrix on the left-hand side to look like this. So we are going to somehow have to change this 2 into a 0. Again, you can't multiply the whole first row by 0. That's not going to work. So what do I need to multiply the second row by? So that way when I add it to the first, this 2 becomes a 0. Well, think. If I multiply the second row by -2 and I add it to the first row, I'll get my new first row. So let's do it. Multiply the second row by -2. And I'm going to add it to my first row. When I combine like terms, I'll have 1, 0, 2, -3. So let's rewrite. We have, this is our new row 1. I have 1, 0, 2, -3. Nothing changed about the second row. And guys, we did it. We ended to our goal. Our goal was to get our matrix in reduced row echelon form on the left-hand side, which is what we did. And now I have my inverse matrix on the right. That was the goal. So we know A inverse is 2, -3, -1, and 2. And we did it. Awesome. All right, I'm going to ask that you guys give example 3 a try. I would pause the video here. Make sure you fully understand these steps. Give example 3 a try, and I'll post my solutions momentarily. All right, so pause the video here. All right, and there you guys have it. So I just went through, I said to pause the video, so you should have given this a try. When you solve for the matrix of the inverse for A, we end up getting 2, 1, 5, 3. So A inverse is the matrix 2, 1, 5, 3. Okay? Hopefully we're finding this helpful so far. All right, so I'm going to show you guys one more way to solve for matrices. So this was one method of solving for a matrix. Now I'm going to show you one more, which you may probably prefer. It's a lot quicker. All right, so we're actually going to solve for matrices by using determinants. So this is another way to solve the inverses of a matrix by using determinants. Again, probably a more preferred method that you guys are going to want to use. So given the matrix A, the inverse of a matrix, this is our formula we're going to follow. So the inverse of a matrix is we take the determinant. So we have AD minus BC. So that's AD minus BC. We take 1 over the determinant of the original matrix for A. We switch A and D. So A and D get switched. So now we'll have DA. and we negate B and C. We negate them. Okay? This is a quick way to solve for the inverse of a matrix. All you got to do then is then just distribute whatever this value is into each one of these values. So let's actually just take a look at an example together. So let's look at exercise 2. The question says find the inverse of a matrix and verify by matrix multiplication that we get back to the identity. Okay, no big deal. So here's matrix A, and we want to find the inverse. Well, the inverse for a matrix is to take the determinant, so it's 1 over the determinant. We switch A and D, and we negate B and C. Okay, so let's actually do it. The determinant for A, so let's find the determinant for A, is going to be 5 times 1 minus -4 times 3. All right, when you guys do the algebra here, I've got what? 5 plus 12, so the determinant is 17. Okay? So, when I find my inverse matrix, I'll have A inverse is going to equal 1 over 17 times, so D and A get switched, so this will be 1 and 5, and we negate B, and we negate C. And guys, all you got to do now is just distribute the determinant. So A inverse will just be 1 over 17, -3 over 17, 4 over 17, and 5 over 17. See how much quicker this is? This is just another way of finding an inverse matrix. Okay? And now the way that we know that this is actually the inverse is just going back and checking. If I multiply A by the inverse and I get back to the identity, we know that this works. All right, so very quickly I will just show you that. So if I were to multiply A, so A times A inverse, I should get back to the identity. So I'll write that over here. If I have 5, -4, 3, 1, and I multiply that by the inverse, I should get back to the identity. All right, we're just doing matrix multiplication here, guys. I have 5 and -4 times this column. So 5 times 1/17 is 5/17. Plus, we have -4 times -3 is positive 12 over 17, which is 17 over 17, which is 1. So there's my first element. Let's keep going. Again, I have first row, now by the second column. Okay, let's see. So we've got, again, I have 5 times 4 over 17. That's going to be 20 over 17. And then I have -4 times 5 over 17. Well, that's -20 over 17. So that's just 0. All right, keep going. I've got 3, 1. Let's pick a different color. Let's do black. 3, 1 and 1/17 is -3/17. So let's multiply those. I'll get, let's see, 3 over 17 plus, we have -3 over 17. So again, that's just 0. And then lastly, when I multiply my last matrix, row and element of the columns, I have 3, 1 times 4/17 and 5/17. So we have 3 times 4 over 17 plus 5 over 17 times 1. So that's 12 over 17 plus 5 over 17, which is just 17 over 17, which is 1. So there you have it. We know that that was the actual inverse matrix because we ended back to the identity. All right, and then the last question we're going to take a look at is exercise 4. Again, we're going to find the inverse by using determinants. Okay, find the inverse by using determinants. So first things first, A inverse is 1 over the determinant. We switch A and D and we negate B and C. So let's do it. We have 2 times 2 minus 4 times 1, which is just 0. Okay, so I'll have A inverse is equal to 1 over 0 times, we switch A and D. So nothing actually changes there. When you switch two 2's, you get back to the same result. And then we're going to negate B and C. And then we're going to distribute. Now, alarms should be going off in your head, like there's something wrong here. Okay? If you guys notice, this is undefined. You actually can't get a determinant of 0. If you get a determinant of 0, this is not possible. Okay? You can't find the inverse of a matrix with the determinant of 0. It's not possible. So because the determinant is 0, we can't find A inverse. Okay? Your calculator is actually going to show you that this is singular. If you have determinant of a matrix is equal to 0, it's called singular. Just some vocab. The determinant, if it equals 0, we use the word singular. So you actually can't find A inverse. Alright guys, I hope you guys found this video helpful. As always, please make sure you reach out, ask questions, etc. This stuff is starting to get a little bit more difficult, as you can see. Alright, I hope you guys have a great day.